In the previous video, we studied refraction and the law of refraction, and we are going to look now at some important applications of this law, in particularly lenses. And lenses, well, we are all familiar with them. Some of you, some of us use lenses to see better, but there's also lenses in microscopes and binoculars, and lenses and projectors and cameras. So there are two types of lenses that we need to know for now, converging lenses and diverging lenses. In this case, light is coming, you have parallel rays coming, and light appears to converge at this point. This is a converging lens. A divergent lens has a different behavior. Light appears to diverge. So the yellow line goes along this yellow ray is traveling along the optical axis. This middle line here that is called the optical axis of the lens. And so for converging lenses, then rays converge towards the optical axis. For diverging lenses, light rays diverge away from the optical axis. Okay, so let's look at converging lenses. A converging lens is typically it's thicker in the center, and the distance from this point to the center, this is called the focal length. And this is a property of the length and depends basically on the geometry of the length. And what happens is if you have, for a divergent lens, sorry, for a divergent lens, then they are thinner here in the middle, and the focal length is the distance from this point to the center of the length, and light appears to diverge from this point. Okay, so this is the behavior of divergent lenses as opposed to the behavior of convergent lenses in which light converges at this point. In here, the rays appear to diverge out of this point here. So thin lenses, uh, there are three situations that we can uh, use to analyze thin lenses. Well, the first situation is when a ray is initially parallel to the optical axis. So you have these rays coming and they are all parallel. So what happens as they get to the lens, then they get refracted and they all converge here. This is your focal distance here. And so this is the first situation. Then another situation that we can have is that, well, light is coming out of this focal point here. So when they get to the lens, then they are all going to travel parallel here. And finally, we have the rays that go through the middle, and these rays don't get refracted at all, so they continue traveling as if nothing happened. So let's see how an image gets formed using a thin lens. So here we have the lens and this is the object. So there are three rays that are important. These are called special rays. One goes straight out of the top, the other goes straight to the bottom, and finally one goes through the middle that doesn't get refracted. So these are the three important rays that you need to draw when you're solving this type of problems. These are the special rays. So this is the focal point here, and this is also the distance to the focal point. You have those two distances here. This S prime is the distance to the image, and S is the distance to the object. So what we know is that these numbers S, F, and S prime, they are related by this equation here, and this is called the thin lens equation. So this equation allows you to get S prime and where the image is going to be located if you know F and you know the image to the object. So that is one of the important equations that are used when designing thin lenses. So then the image that you see, depends on where this plane is located. If this plane is not exactly here, then your image is going to be blurry. So if you look at this point P prime here, we're going to take this point P prime and magnify that. That is right here. Right at this point, all the rays are converging, and then you're going to see a very sharp image if you have your plane here. However, if you move that plane a little bit off this distance, then the image is going to be blurry. So, and what you're doing here is basically focusing the image. So how do you do that? Well, you can move the plane to focus an image. You can move the image, the object, or you can move the lens. If you move either the plane, the lens in this direction of the object, you can get a sharp image here. You can get to have a sharp image, which is what you want when you're designing lenses. So these are to solve problems that involve thin lenses. Well, you are going to start by drawing a picture in which you draw an optical axis. Then you center the lens on the axis. Then you represent the object with an upright arrow at a distance s. And then you draw the three special rays. These three special rays are this one, and this one. You draw, so you draw those three special rays, and then uh, you extend the rays until they converge. So basically you draw them, and then this is going to get refracted and converges here. This is going to continue straight and converges here. And this is going to continue this way and converges here. So you draw these three rays until they converge and you have to take into account the refraction. And then you measure the distance s prime, and that's typically what you want. And also you can measure the image height relative to the object height. So magnification or lateral magnification is basically how much bigger you see the image, how much bigger is the image related to the object, and it's given by minus s prime over s. Remember that s prime is this distance to the object here, and s is this s prime is the distance to the image, s is the distance to the object. So this gives you the lateral magnification, and a positive value indicates that the image is upright relative to the object. Negative value indicates the image is inverted relative to the object. And the absolute value gives this ratio here. Okay, so now we know the thin lens equation, which is given here. And we know also how to calculate the magnification. So what happens to the virtual image then? Well, imagine that you have this object here, right? And then you put a lens here and you want to see on the other side here, right? You're looking here. So then this is your real object. This is what you're seeing here. And then if this object this is your focal point here, right? So if this object is in between the focal point and the center is somewhere here, then light coming from this point is going to look as if it was coming from here, right? So this is a ray here, and then light coming through this point here is going to look as if it was coming through this ray, and same here. So what you're gaining here is a magnification, right? A magnification, and this is basically what it happens. This is your eye here, And then what you're going to see is that this green object is going to look bigger here in your eye. So this is exactly what you do with magnifying glasses or a microscope or binoculars. So there is one more. We can also have a similar equation or analyze divergent lenses. There's also three situations here. A ray initially parallel, then you have this ray coming that is parallel, goes through the divergent lens, and the light diverges. So it looks like all these rays on this side, they look as if they were coming from this point. Or you can have divergent rays, and then what is going to happen is that they are going to become parallel rays. This is your focal point here. And finally, you're going to have the rays that go through the middle and they don't get affected at all. And we can do a ray tracing analysis of divergent lenses. And so we are going to basically draw the same special rays as we did before. And then we are going to trace the divergent rays backwards and measure the image distance, which is what we want. Okay, thank you.